Welcome to another video on the basics of model theory. Today's video is about a certain class of beautiful first-order theories with many different characterizations, namely countably categorical theories. A first-order theory T is called countably categorical or omega-categorical if all countable models of T are isomorphic. A structure is called omega-categorical if its first-order theory is omega-categorical. All finite structures are omega-categorical because the first-order theory of a finite structure completely describes the isomorphism type of the structure. And we will see that omega-categoricity can be viewed as a finiteness condition for infinite structures. One of the prime examples of an omega-categorical structure is Q, the rational numbers, with the usual strict order on Q. This is an immediate consequence of Cantor's theorem, which states that all countable, unbounded, dense linear orders are isomorphic. This can be shown by a back and forth argument that we have seen in an earlier video. There are many more examples. The class of omega-categorical structures is very large and rich. The theorem of Engeler, Ryll-Nardzewski and Svenonius provides many different looking characterizations of omega-categoricity. Let B be a countable structure. In this video, for simplicity, I also assume that the signature is countable. But there are more general forms where this assumption is not necessary. The theorem provides equivalent characterizations of omega-categoricity of B. I have picked out 8 such characterizations, but there are more. I present them step by step, since all of them won't even fit on the screen. There's one cluster of characterizations related to atomicity of models. Atomicity was the topic of the previous video. There's another cluster of characterizations related to saturatedness of models. Saturated models were the topic of another earlier video. Finally, there's an important cluster of characterizations related to symmetry of models. In fact, we will see that omega-categoricity of B is a property of the automorphism group of B. We start with the characterizations of countable categoricity based on atomicity and related concepts. Recall that a structure is called atomic if it only realizes principal types, that is, types that are isolated by a single formula. We will prove that a structure B is omega-categorical if and only if every type of B is principal. And this in turn is equivalent to the condition that every model of the first-order theory of B is atomic. We prove these equivalences in cyclic order, showing that 1 implies 2, that 2 implies 3, and that 3 implies 1. For the implication from 1 to 2, we show the contrapositive. So suppose that P is a non-principal type. The theory of B has a model B1, where P is realized. Every type can be realized, even in some elementary extension of B. And using the theorem of Löwenheim and Skolem, we may even assume that B1 is countable. But since P is non-principal, by the omitting types theorem from the previous video, there is also a model B2 which omits P. That is, B2 does not realize P. And the proof of the omitting types theorem shows that we may even choose B2 to be countable. So the two structures B1 and B2 cannot be isomorphic. But both of them are countable, and they have the same theory as B. So B is not omega-categorical. For the implication from 2 to 3, we assume that every type of B is principal. So in particular, B and any other model of B does not realize any non-principal types, because there are no non-principal types. And this is precisely what it means to be atomic. So all models of the first-order theory of B are atomic. For the implication from 3 to 1, it suffices to remember a statement from the previous video. Any two countable atomic structures with the same theory are isomorphic by a back and forth argument. So So if all models are atomic, all countable models of the theory of B must be isomorphic. In other words, B is omega-categorical. We now state the second cluster of characterizations linking omega-categoricity with saturatedness. Characterization number 4 of omega-categoricity is one of the mentioned finiteness conditions. B is omega-categorical if and only if B has finitely many complete n-types for each n. It is also equivalent to the property 5 that there are finitely many inequivalent formulas with free variables x1 up to xn. Finally, omega-categoricity of B is also equivalent to the property that every model of the theory of B is omega-saturated. We prove that 2 implies 4, 4 implies 5, 5 implies 6, and then 6 implies 1, which we already know is equivalent to 2. So this shows that indeed all these properties are equivalent. Recall that 2 states that all types of B are principal. The implication from 2 to 4 is an immediate consequence of the compactness theorem. Let phi I be formulas isolating the complete n-types of B. So these formulas exist since the complete n-types are principal. Then the theory of B, together with the negation of all of the phi I, is clearly unsatisfiable. So by the compactness theorem, there is a finite subset of those formulas, which is, together with the theory of B, unsatisfiable. Therefore, in every model of the theory of B, every n-tuple must satisfy one of the formulas from this finite set of formulas. And since each of these formulas isolates an n-type, we find that the theory of B has finitely many complete n-types. And this concludes the proof that 2 implies 4. For the proof that 4 implies 5, we assume that there are finitely many complete n-types. Note that this implies that there are finitely many not necessarily complete n-types. The reason is that every n-type is completely determined by the set of complete n-types that contain it. So if there are finitely many complete n-types, there must also be finitely many n-types. Finally, the number of n-types clearly provides an upper bound for the number of inequivalent formulas, because every satisfiable formula with free variables x1 up to xn is in particular an n-type. This concludes the proof that 4 implies 5. For the implication from 5 to 6, we have to show that every model of the theory of B is omega-saturated. So let A be a model of the theory of B. Let little a be an n-tuple of elements of A, and let P be a complete one-type over A with parameters from little a. What we have to show is that P is realized in A. By assumption, there is a finite number of inequivalent formulas, phi, with free variables, x1 up to xn plus 1. We pick out all those formulas, such that phi x1 A is in P. Then we take the conjunction over all those formulas. The resulting formula clearly isolates P. So P is a principal type, and hence must be realized in A. And since A and P were chosen arbitrarily, this proves that A is omega-saturated, and concludes the proof that 5 implies 6. For the proof that 6 implies 1, recall that all countable omega-saturated structures that have the same first-order theory are isomorphic. This was a lemma proved in a previous video about saturation via back-and-forth argument. Therefore, all countable models of the theory of B are isomorphic. In other words, B is omega-categorical. We are not yet done with the theorem. 2 very important characterizations of omega-categoricity are still missing, namely those related to symmetry. I already mentioned that the omega-categoricity of B can be expressed in terms of the automorphism group of B. I need to introduce one concept from permutation group theory, namely the concept of an orbit. Let G be a permutation group. That is, a set of permutations on a set B, which contains the identity map on B, is closed under taking inverses, and which is closed under composition. The orbit of an element, little b of capital B, in G, is the set of all elements of B of the form alpha applied to little b, for some permutation alpha from G. Note that the orbits of G form a partition of the set B. Similarly, the orbit of an n-tuple, little b, of elements of capital B is the set of all images of that n-tuple under permutations from G, applied component-wise. That is, we compute from the n-tuple b1 up to bn a new n-tuple alpha b1 up to alpha bn. Characterization 7 of omega-categoricity requires that every relation over B of some arity n that is preserved by all automorphisms of B is definable in B by a first-order formula. So there exists a first-order formula that holds for precisely the n-tuples that lie in the relation. Our final characterization, number 8, is also phrased in terms of the automorphism group. The structure B is omega-categorical if and only if the automorphism group of B has only finitely many orbits of n-tuples for every n. Permutation groups with this property are called oligomorphic. So this is a property that is expressed purely in terms of permutation groups. There's no reference to first-order logic anymore. There are many reasons why first-order logic is the most important logic of all logics. For me, one of the reasons is this tight link between first-order logic and permutation groups. We will prove that properties 2, 3, and 5 combined imply 7. That 7 implies 8. And finally, it is fairly easy to go back to 5. Remember that 5 is the property that there are only finitely many inequivalent formulas phi, with 3 variables x1 up to xn. So 8 implies 5 simply because of the fact that automorphisms of a structure preserve all first-order formulas. So n-tuples that lie in the same orbit satisfy the same first-order formulas. We are really left with the task to prove 7 and then to prove 8. To prove 7, let R be a relation of arity n over B that is preserved by all automorphisms of B. Then R must be the union of orbits of n-tuples in the automorphism group. I claim that the orbit of an n-tuple A is determined by the type of A in B. Here I use atomicity of B. This is item 2 of the theorem. If two tuples in a countable atomic structure have the same type, then we can make a back and forth argument to construct an automorphism of the structure that maps one tuple to the other, so the two tuples lie in the same orbit. Now, observe that the type of A is determined by a first-order formula. This is by assumption 3. All types in B are principal. Finally, we obtain a definition of R by taking a disjunction over all those formulas for all the orbits of n-tuples that lie in R. This is because there are only finitely many inequivalent formulas with 3 variables x1 up to xn over B by item 5 of the theorem. This disjunction is then the desired first-order definition of R in B. For the implication from 7 to 8, we show the contrapositive and assume that there are infinitely many orbits of n-tuples in the automorphism group of B. Note that arbitrary unions of orbits of n-tuples are preserved by the automorphisms of B. So we have 2 to the omega many relations over B of arity n that are preserved by the automorphisms. This means that some of these relations are not definable in B. Here we use our assumption that the signature is countable. This implies that there are only countably many first-order formulas with 3 variables x1 up to xn. By the infinite pigeonhole principle, some of the uncountably many relations preserved by the automorphisms do not have a first-order definition. We close this video with a couple of illustrations how useful this theorem is to check whether a given structure is omega-categorical. Consider the structure Z of the integers with the usual linear order on the integers. This structure is not omega-categorical. We have already seen in a previous video that there are countable linear orders that are not isomorphic to Z, but satisfy the same first-order theory as Z. One example was obtained from taking the union of 2 copies of Z and making all points from one copy smaller than all points from the other copy. Therefore, Z is not omega-categorical. Another way of seeing this, using the theorem of Ryll-Nardzewski, is by counting orbits of the automorphism group of Z. This permutation group is particularly easy. It just consists of the shift operations x goes to x plus c for some integer c. The number of orbits of this group is 1. In other words, this permutation group is transitive. Every point can be mapped to any other point by an automorphism. However, the condition 8 in the theorem of Ryll-Nardzewski states that the number of orbits of n-tuples must be finite for all n, not just for n equals 1. So let's have a look at n equals 2. Let's count the number of orbits of pairs. For example, let's have a look at the pair 1, 3 and the pair 1, 4. I claim that these pairs do not lie in the same orbit. To see this, consider the formula there exists y, which is strictly larger than x1 and strictly smaller than x2. And there exists only one such element. This can be said by a first-order formula. We require that every z, which lies strictly between x1 and x2, must be equal to y. This is a formula that holds for the pair 1, 3, but does not for the pair 1, 4. It follows that there is no automorphism that maps the pair 1, 3 to the pair 1, 4, because automorphisms preserve first-order formulas. In general, a pair xy can be mapped to a pair uv if and only if x minus y equals u minus v. Since there are infinitely many possible differences, there are infinitely many different orbits of pairs. So the theorem of Ryll-Nardzewski implies that the structure Z is not omega-categorical. Let's have a look at another example. Consider the structure Q plus of the rationals with addition. I claim that this structure is not countably categorical. Here I find it more convenient to use orbit counting to prove this, rather than constructing a countable non-standard model. The automorphisms of Q plus are of the form x maps to c times x for some rational constant c that is not 0. Thus, all rational numbers that are distinct from 0 lie in the same orbit. And 0 is the only element that satisfies the formula x plus x equals x. So we have exactly 2 orbits. In order to prove that the structure is not omega-categorical, we again have to look at orbits of pairs. A pair xy can be mapped to a pair uv of rational numbers if and only if x divided by y equals u divided by v. Therefore, there are infinitely many orbits of pairs of non-zero elements. The theorem of Ryll-Nardzewski, item 8, implies that Q is not omega-categorical. I also have an example that illustrates how to use the theorem of Ryll-Nardzewski to prove that structures are omega-categorical. In fact, the following example is an entire class of examples. A very rich class of examples. Let B be a countable homogeneous structure with a finite relational signature. Then B is omega-categorical. This covers our first example, the ordered rationals, which is a homogeneous structure and which has finite relational signature. But it also covers many examples of homogeneous structures that we have seen in the video about amalgamation classes. For example, the random graph, the countable universal homogeneous tournament, the countable universal homogeneous poset, or the countable universal homogeneous Kn-free graph. For finite relational signatures, for every n, there are only finitely many non-isomorphic substructures with n elements. Homogeneity then implies that there are finitely many orbits of n-tuples. And the theorem of Ryll-Nardzewski then implies omega-categoricity. A few words on the assumptions. We require that the signature is finite and relational. Both assumptions are necessary. Consider, for example, the class C of all finite structures with a countably infinite relational signature. Then clearly, this class is an amalgamation class. We even have the free amalgamation property. So there exists a countable homogeneous structure whose age is precisely C by Freise's theorem. But this structure is not omega-categorical because it has uncountably many non-isomorphic substructures. For each relation R and every element X, the tuple XXXXX might be in the relation or not. So we even have uncountably many one-element substructures. All these non-isomorphic structures correspond to distinct orbits. So by the theorem of Ryll-Nardzewski, the structure is not omega-categorical. Also, the assumption that the signature is relational is necessary. I have defined homogeneity only for relational signatures. But the correct definition for general structures B is that B is homogeneous if every isomorphism between finitely generated substructures of B can be extended to an automorphism. Consider, for example, the structure whose domain is the natural numbers with the constant 0 and the successor function. I claim that this structure is homogeneous. Any isomorphism between finitely generated substructures must fix 0, it must fix S of 0, it must fix S of 0 and so on. It must fix any natural number. And clearly the identity map can be extended to is an automorphism. So yes, this structure is homogeneous. But clearly the structure is not omega-categorical because it has infinitely many orbits of points. In the next video, I will present several techniques to construct omega-categorical structures.